Good day and welcome to this video covering part one of three-dimensional space. Now, in Calculus 3, kind of a big overarching goal is to take some of these key ideas from Calculus 1 and Calculus 2, things specifically differentiation and integration, and extend them from the well-known and very familiar two-dimensional space to three-dimensional space where we have functions of more than one variable. So to get started, what we have to do is provide kind of a basic overview of this geometry of three-dimensional space and really think of this as kind of laying the groundwork for what is to come. If we want to use this space to talk about differentiation and integration of functions of more than one variable, we really need to understand how it works. So we begin with recalling the basics of two-dimensional space. So in two-dimensional space, we're thinking we have this plane determined by an x-axis and a y-axis. And we oftentimes refer to this as R2, where we use kind of this fancy script R, and it's supposed to indicate two-dimensional real space. Each point in R2 can be represented as an ordered pair, A comma B, where remember what these quantities are measuring. We think of B as being some directed distance from the x-axis, whereas A represents a directed distance from the y-axis. And the observation to make is that each point in R2 can be represented as a pair. And because each point can be represented as a pair, this is why we refer to the plane as two-dimensional. So we'll say R2, or kind of the XY plane, is two-dimensional. And what we're going to do is take this idea and extend it to three-dimensional space. So now instead of having just an x and a y axis, we're going to need to include a third axis. Now, as we will find out as the semester progresses, the real difficulty here is we're trying to draw three-dimensional objects in two-dimensional space, which requires practice. We think of this x-axis as coming directly out of the screen towards us, the y-axis, and the z-axis. Similar to R2, since we have three dimensions, we'll refer to this as R3. And if we pick any point we want in three-dimensional space, we can now represent it as a triplet, A, B, C, where the A, B, and C are the x, y, and z coordinates, respectively. And what we think of these as measuring is once again kind of distances. We think of that C quantity as measuring how far the point is sitting above the xy plane. We think of B as measuring how far that point is away from the xz plane. And then we think of the A as measuring how far the point is away from the yz plane. So you can see there's this almost three-dimensional grid in play. And similar to our observation above, each point in R3 can be represented as a triplet. So that would be as A, comma B, comma C, which is why we refer to this as being three-dimensional space. And throughout our discussion today, we'll be making connections or analogies back to our experience dealing with two-dimensional space in previous courses. And one very basic observation to make is that the x and the y-axes break up two-dimensional space into four quadrants. And there is a very similar idea going on in three-dimensional space, except now it's what we will refer to as the three-dimensional coordinate planes. That is to say, we have the xy plane, which we think of as this plane determined by the x and the y axes. We also have the xz plane, which we think of as being determined by the x-axis and the z-axis. So it's kind of coming straight out of the board at us. And then flat in the board or flat in our screen would be the zy plane. So we have these three coordinate planes, and they divide three-dimensional space into 8 octants. And of all of those octants, there's typically only one that we ever refer to. We will oftentimes refer to or restrict ourselves to work in the first octant, oftentimes mainly for convenience, where the first octant we think of as being x, y, and z, where all of those quantities are strictly non-negative. And if we wanted to draw a picture of what that looks like, the first octant just does not include the negative axes. So we think positive x, positive y, positive z. And when it comes to three-dimensional space and sketching graphs, we need to think about how we build this up from two-dimensional space. When we are dealing in two-dimensional space, so let's just make kind of the observation here, we typically think of y being a function of just x, and the graph is a curve. In three-dimensional space, the graph of a function involves 3 variables. So what we're thinking in three-dimensional space is now we have z equals f of xy, and the graph of such a thing is called a surface. And that language of saying we have a surface is very important. Whenever we see that wording, it very clearly indicates to us we're going to be dealing with three-dimensional space. And a common question that we can now ask you is to graph the surface given to us by some equation. And the key here, once again, is to realize that the surface wording, that indicates that we're dealing in three-dimensional space. So the first thing we would need is our coordinate system. So our generic coordinate system that we would typically draw, unless we're being restricted to the first octant, something like this. The x-axis coming out of the screen directly towards us, y-axis, z-axis. And one way to think about this is to put it more into what we might think of as sit notation. So the observation is this surface x equals 3 is made up of a bunch of three-dimensional points. So they're all of this form x, y, z. And the restriction placed on them is that x is equal to 3. And if this is the only restriction placed on the surface, what does that tell you about y and z? What it tells us is that y and z can be anything. So we are looking for all points of the form, 3 comma something, something. So in terms of maybe the simplest possible point, that would be 3 comma 0 comma 0. So 3 units out on that positive x-axis. And remember what that x coordinate is measuring for us. How far we are away from the yz coordinate plane. And if that x coordinate is always 3, we have all points 3 units away from the yz plane. So that would be a copy of this yz plane just pulled 3 units out towards us. So to sketch this, we have to be a bit careful. It's once again, as a reminder, it's difficult to sketch 3 dimensions on a 2-dimensional blackboard, paper, or tablet. So here what we're thinking of is we have a plane, and every point on this plane is 3 units away from the YZ plane. So I would describe this in words as saying it's a plane parallel to the ZY plane. And something you hear me tell you over and over again throughout this semester is our pictures do not have to be perfect. Far from it, as you can see from our first couple pictures here. They just have to get that relevant information across. If I've noted that it's a plane parallel to the XZ plane, and I've included a specific point on it, that should do the job. And let me finish by just making one quick kind of analogy to what we've seen in the past. So the R2 analogy would be that x equals 3 is a curve, not a surface. That's why the language here is so key. And that curve, x equals 3, would be represented graphically as a line. And that line, x equals 3, indicates all possible points that are 3 units away from the y-axis in that positive direction. And that finishes part 1 of our videos for three-dimensional space. So stay tuned for the next video and take care.